Okay, welcome everyone. Let's get started, and we always start live by sharing the screen, and I think I have now managed to do this. Okay, let's make it full screen. Okay, so what we will do today in this video is I would give you an overview of the subject of machine learning. I'll try and go through what are the different concepts that we will start with, and where different ideas in machine learning people are working with fit in. I have called this lecture zero, so it's zero because we have really not started, not because I program in Python and arrays start with indexing zero. We will start with a very, very broad overview. This is a very simple overview. I only have 2 slides here. As you can see, slide 1, only 2 slides here. Okay, so the idea of machine learning is about what one would describe as data-driven modeling. So modeling is something you would all be familiar with in one way or the other. The idea of modeling is, if you think about architects. So architects would want to build, you hire an architect to build a nice building. The architect would not immediately build the building. They will go and build a little scaled down model of it, and then look at this model, and if this model looks good, then they would go and build that building. If this model looks ugly, then hopefully they won't go and build this building. Think of an engineer who wants to build a bridge. What would they do? They would go and build a scaled version of this bridge. Maybe they will hit it with some force, and if it collapses, then they won't build the bridge. And if it stays, then maybe they will go and build the bridge. You can think of modeling in mechanistic ways. So there are models of economy, there are models of air pollution, how air pollution propagates. There are models of climate change. These are models built by people who have huge amounts of domain knowledge, or who think they have huge amounts of domain knowledge. They would look at relationships between variables, how pressure affects temperature and so on. And they would write differential equations that describe how different variables in the system might interact. And then they might go and solve these differential equations. And if they can solve them, the solutions are what they use to either explain the world or make predictions about what might happen tomorrow, what might the weather be like tomorrow. Or they might use these models to ask what if type intervention questions. So you take this model and say, what if I kill part of this variable and or reduce this variable, or if I give a certain amount of drugs, what might the response of the patient be? So you can ask that kind of what if questions. In machine learning, we work with data-driven models, and what I mean by that is that the problem is posed to me in terms of data. So there are capital N data items here. Someone gives me data as a way of posing the problem. So you can think of X and T as some input going to a system, and T as the target that this system has to deliver or achieve. And there are N of them, and that is how you have specified to me the problem. Now, when you specify this problem, you can think of X going into a system, like I said, and T coming out. Sometimes this T can be labels. So out of your system sees, your system is a camera, and this camera sees some pictures, takes some pictures, and your task is to classify or say if what is seen in this picture is a tree or a lamppost or a car or an old lady crossing the road. You are solving, in that case, a classification problem. You take some data and you're going to classify that data into one of many categories. Sometimes the T is continuous valued. So it could be temperature tomorrow. It could be stock market stock price tomorrow. And in that case, you're solving what's known as a regression problem. You're predicting a continuous valued function, continuous valued variable based on these inputs. It's a regression problem. Both these problems, classification and regression problems, fall under the general umbrella of supervised learning problems. So by supervision, we would mean there is a problem, there is a learning problem, and the target given to you is kind of a supervision signal that tells you how best to go about doing this. There sometimes are problems in which you only give me the X's. There's no target associated with them. And these are known as unsupervised learning problems. problems. And even in this case, when there is no targets associated with it, by having this collection of data, these n items in some multidimensional space, I might be able to say something about the mechanism that generated this data. So here are examples of what I might be interested in. I might be interested in asking, how is this X distributed in this space? Is it a lot in this corner and a lot there? Or is it uniformly across the whole space? Or is there some cluster structure? Is this X only found in a small part of this space in very tight clusters? Can I identify those clusters? Is there some reason why there is a cluster structure? I could ask that kind of question. Sometimes I might ask questions like saying this X is measured in a high dimensional space, but not all those measurements are necessary, and all the useful information relating to this problem actually lie in a lower dimensional subspace. If that is the case, then I might be able to make some statement about that data generating mechanism by projecting this data either linearly or non-linearly onto a subspace and analyzing this data in that subspace, thereby making a statement about the problem. Now, if, of course, you can imagine if that subspace is dimension 2, then you have the advantage, you can even visualize this data. So that's an important topic in machine learning data-driven modeling, visualizing. And that group of problems where there is no target specified to me is known as unsupervised learning problems. There is no supervision target, so it's unsupervised. There are some fascinating problems that are around today, which is a mixture of these two. So labeling, finding the targets for some things might be very, very expensive or time consuming. In that case, you will be in a situation where some part of the data is given as supervised paradigm with target specified. And in that same domain, there's a huge amount of data that is not labeled, with which there's no target associated with it. So you might ask questions like, can I build a system that learns the relationship between X and T in a supervised setting, but take advantage of the fact that there is a lot of unsupervised data, unlabeled data, in order to boost the performance of this? And we will see examples of that later in the course. And these combinations like that are known as semi-supervised learning problems, partly supervised, partly unsupervised, so it's semi-supervised. Now, staying with this domain of X and T specified, let's see what we can do would be to ask the question, can I use some way of fitting functions through this X and T? What I would start with here is the belief that the relationship between X and T, X goes in T is the target, this relationship is not that this data is coming from some random process, it is coming from some underlying physical mechanism that's generating this data. And because there is some underlying physical mechanism generating this data, there's some regularity there. And that regularity would let me fit a functional relationship through xt in that space. And this function could be parameterized by some parameters theta. So I start with the belief that there is some physical system that's generating this data. And because there is a physical system generating this data, there are some smoothness properties associated with this data. And because that process is smooth, I might be able to fit a function through this, and this function could be parameterized by theta. It could be linear, it could be nonlinear. And we'll deal a lot with nonlinear problems, nonlinear functions in machine learning. And then there's some noise associated with this as well. So not all the data is generated by such a function, but there is some noise in that process. So theta are parameters of this function, and x to t has a functional relationship. And if I didn't have this belief, I don't have a start in machine learning. This is one of the basic things from which we get started. Now, once I think I can fit a function that's parameterized by theta, the next thing I would do is, how do I fit this? What are the values of parameters? Because you have only given me the data. And I would do that by doing parameter estimation. What would I do? I would go and ask the question, on every single data point, x of n, t of n, what does the function give me for some values of theta? What is the target that you gave me? The difference between the target and the function output is an error. I would square this error and sum over all the data that you gave me. I have decided, I have written here, an error that I make at a particular value of theta over the data that you gave me when I fit this function. Okay? And then I can now ask the question, what would be values of theta which would minimize this error? What's the best fit I can have of this function through the data that you gave me by tuning the values of theta? And there's a whole bunch of optimization algorithms we will study with which we estimate parameters of this kind of parameters theta. Now, once I estimate parameters of this theta, I'm going to do something with it. What am I going to do? I'm going to make predictions. And the predictions I make would be, can be written like this. Now, the prediction I make of a target at n+1 is the function evaluated at the input n+1. And the parameters that going into this are the theta hats. These are the best parameters I worked out by optimizing, minimizing this error. Now, note this is a very important property, important point, that the data you gave me runs 1 to n, and the prediction I'm making is on capital N+1. Yeah? The predictions I make to be of use, to be of interest, are on data that I have not seen before. So you gave me n data to make a model, and the model I make is by fitting a function, and the process by which I do this is by minimizing the error, and I get a value of parameters to minimize this error. And once I have these parameters, I make predictions on data that I have not seen before. This is important, okay? Sometimes you will find that I can just by increasing the power of this function, by making a more and more complex model with millions of parameters, I might be able to fit any data that you give me. Yeah? So, and thereby running this error down to 0. An extreme version of this, of course, is just my function is just a lookup table in which I have stored all the data that you gave me. Now, something like that is not capturing any of the smoothness properties, so it is unlikely to perform well on data I have not seen before. So I want to then control the function from being too complex. I want this function to help me make predictions on unseen data, and I do this by a trick called regularization. What do? I write out an error which partly consists of error on the data that you gave me, and partly a regularizing term that penalizes this theta from taking arbitrary values, okay? So now the error that I minimize has two parts. One part is coming from the data that you gave me, so it's summed over all the n's. The other part is coming from some constraint or limitation or penalty that I'm going to throw on the parameter values that come out of this, okay? Now, that is done as a way of restricting the complexity that this function can achieve. But there's a little bit more to it than that. Remember when I started talking about this, I said, you have specified to me a problem just by giving me some data. But in that domain in which this data came from, there is also some prior knowledge about what's happening, what's this system about, what are things it can do, but cannot do, and so on. This regularizer is a place where I have a chance of injecting some prior knowledge about that problem domain. So there are ways in which I can choose this regularizer so that the function that I learn out of this could be a smooth function. There are tricks by which I can choose this regularizer so that the function that I learn is a sparse function. A sparse function means it's only dependent on a small number of these parameters, not on all of them. So it may well be you would have made lots and lots of measurements to go into the input in order to specify this problem. But I might, as an expert, come in and say, hey, all those problems, all those variables that you have measured are not necessary. Some of them have to be thrown out, and thereby giving you a simpler model. And if I had prior knowledge that that might be the case, then I have a way of tweaking this regularizer in order to achieve this. And when we go to week 4, week 5, we will learn precisely what techniques by which we can do this. So injecting prior knowledge comes in here, and this is a convenient way by which I can achieve that. Often when I do this process by fitting functions through the data you give me, there's a lot of uncertainty associated with this. So there are situations where I have no idea what this model that I want to fit is. There's a lot of noise in the process, and the learning algorithms that I use also have uncertainties associated with this. And what I would then do is to model the uncertainties that are going on not by estimating one set of values for the parameters, but defining a probability density over these parameters conditioned on the data that you gave me. So this is a probability density written on top of the parameters. So there's a distribution of these parameters, and that's conditioned on the data that you gave me. And this distribution would enable me not just to make predictions of the target on unseen data, but because I have a distribution here, to make a predictive density. So I can define a distribution over that target that I'm trying to predict on unseen data. A simpler version of this I won't just give you a prediction, I would also give you, along with the prediction, an error bar on this. How confident am I of this prediction? And that confidence measure that I give you would encapsulate all the uncertainties that I would have come across along the way in which I have done this task. Yeah, so we'll see examples of this as well. So how do you make predictions from such functions, from such densities? Often we would be using expected values of some functions of the theta. So the theta has been learned. What has been learned is a probability density over this theta. And your prediction will be some function of that theta. And you would want to calculate an average. On average, what do I predict? And of course, you might know from primary school that if you want to calculate the expected value of a function of a variable, then you integrate this function weighted by the probability density, and you integrate out over the entire space. Okay, this is how you calculate averages. Expected values are the variable multiplied by, or variable function of a variable multiplied by the probability density and integrated across the whole thing. We'll see detailed examples of these as we go into the course. Now, as soon as someone writes an integral, you know from childhood that differentiation is something all of us can do. Integration is difficult. Yeah, not everyone can do integration. Even the smart guys can't do integration. Yeah. So when you can't do this integration, what we do is we resort to numerical methods of doing integration. So what we will do is we will draw many, many examples of theta from the density P of theta, and then calculate the function g at all those values theta and average it. Okay. So that's like you have a probability density. You want to calculate an average of some function of the variable. And because we don't know how to integrate, what do? We draw samples from this. So in regions where the probability density is high, I would draw more samples. In regions where the probability density is low, I would draw fewer samples. Then I will get a weighted average of the effect of that probability density on the prediction that I'm going to make. Okay. And there's a huge body of literature around this. How do we sample from a difficult probability density, and how do we do these averages? There is a relationship, fundamental law that tells us that the accuracy with which you can approximate this integral with this summation is dependent only on the number of samples that you draw and not on the dimensionality of this theta. And that's a relationship that we might hit later in the course, which makes this whole thing tick, as an aside. Okay. Another important thing that we'll come across in data-driven modeling is sequential estimation. So I told you here right at the beginning that we are going to start with someone giving us all the data, capital N data to me. Sometimes, just to make my life hard, or there might be very interesting problems that are associated with this, you might give me this data one at a time. So you will give me data sequentially one at a time, and you would expect me to learn something from the data I have seen up to this point in time, and then make a prediction next point in time when you give me just one more data. Okay. So this fits into this kind of structure. So I have an estimate of theta at time n-1 using all the data I have seen up to time n-1. From this, I would make a prediction of what this theta might be at the next point in time, but using all the data that I have seen up to the past point in time. So that's a prediction step. And then the next point in time, I get some new data, and then I would correct my prediction and get the value of theta at time n using all the data up to and including time n. So a prediction step followed by a correction step. Okay. And that fits into a very nice framework where if the underlying dynamics that I'm dealing with is linear, and the disturbing noise, such as the noise that you see here, is Gaussian distributed, then I can do this optimally by a technique known as common filtering. If any one of those is relaxed, that is, if the noise is not Gaussian, or if the dynamics that I'm dealing with is nonlinear, then I cannot do it optimally with Kalman filtering in closed form. What I will resort to is this kind of sampling method, but cast in a sequential setting, and that touches on the topic of particle filters. So Kalman and particle filters, we may not touch this in this course, but we will lay the foundations for seeing this in online learning course later in the second semester. So the only point is that this is a sequential setting as opposed to the setting in which I saw all the data in one go. A very closely related topic, and there's a specialist module on this next semester, is called reinforcement learning. And this addresses not just static prediction problems of classifying, regressing, or even density estimation. This relates to problems that are planning problems. So think of game playing, think of a game of chess. So in pattern recognition problems, you are shown a picture and told there is a bicycle on it. Another picture and told there's a car on it. Another picture and told there's a lamppost on it. So those are problems in which you are immediately told what the supervision signal is, from which you can learn something. In gameplay, in a game like chess, for example, if you want your computer to play chess, then you make a move, you don't know what's happening. Your opponent makes a move, then you make a move, your opponent makes a move, and once you have made 30, 40 moves, you then know that you have won or you have lost. So your reward, your knowledge of whether this move that you're going to make now is going to lead to a winning position or not is going to happen after 40 steps, and you do not know what's going to happen in between those 40 steps. Yeah, so that immediately becomes a planning problem. And once you have made the 40 moves and know that and find out whether you have won or lost, then the reward that you get, you have to propagate backwards and ask the question, how much of that is going to attribute to here? That kind of planning problems are in the subject of reinforcement learning. And this topic has hit the headlines quite a lot recently. You might have seen in the press that we can now beat the chess champion in using computers. You can beat the world's Go champion in computers. I read last few months ago that the world's Go champion has now stopped playing Go because the machine is so good. And the underlying technology that drives that is the subject of reinforcement learning, which we won't touch on this module, but there's a specialist module on this next semester. So that is a one slide overview of just about everything in machine learning. So it's the world's shortest tutorial on machine learning, I claim. Almost anything that you see as recent development in artificial intelligence in general, the driver behind all the recent developments in artificial intelligence is the subject of machine learning. And just about anything you can find in machine learning will fit somewhere here. And many of us researchers in the subject are interested in various questions like what type of function do we fit in? So in the past, we were dealing with neural nets. Now we are dealing with deep neural nets. What are algorithms by which we can estimate parameters? How reliable are they? Do they get stuck in local minima, or can we optimize them properly, then get global solutions? We may be interested in asking what are good regularizers through which we can inject prior knowledge of the problem domain. We'll be asking questions like how do you characterize uncertainty of predictions that we make, and what are sampling methods by which we can draw things from very complex probability densities, and how do we solve pretty challenging reinforcement learning problems that are planning problems with which we can optimize some planning actions. So we'll stop here. This is just a one slide introduction to the whole of the subject, and we will get started with lecture 1, in which we will go into little bits of these bit by bit. So I will stop sharing now, and thank you very much for listening to lecture 0.